realized.
We have ignition, and we have liftoff.
The initial calculation showed that we were going to be in great danger of getting really fuzzy pictures if we didn't do something to the spacecraft.
Voyager to turn its camera back towards Earth, and it was basically amounts to Earth's first ever selfie.
For almost 5 decades, Voyager 1 has voyaged through the universe, beaming back newfound knowledge to Earth. However, its latest discovery has shaken the foundation of our understanding. The space probe recently detected something mind-blowing, sparking intense debate among scientists worldwide. This groundbreaking revelation was kept hidden until deGrasse Tyson, a renowned figure, unveiled it to the public. But what precisely are these mysterious objects, and what implications do they carry? Join us as we explore how Voyager 1's detection of 500 unknown objects traveling through space has revolutionized our understanding of the cosmos, the terrifying space discovery. NASA's space probe, Voyager 1, has recently made a horrifying detection of 500 mysterious objects passing by in space, leaving scientists in shock. This revelation caused a stir, raising lots of concerns among researchers who were working on the project. Although it is normal for Voyager 1 to encounter some object in outer space, this discovery is very different. The mysterious signal and oddity in the message Voyager 1 sent back to Earth came as a surprise to the researchers. The space probe started sending telemetry data back to Earth, but the reading was unusual, and researchers couldn't understand what it signified. They named the phenomenon an anomaly, seeing they could not decipher the message the probe was trying to pass. Despite the transmission, Voyager 1 continues to respond to commands from mission control, but with a slight delay in communication, which only adds to the puzzle. What was particularly strange about this anomaly was that it did not set off the probe on the board fault protection system. The systems are developed to trigger when anomalies are discovered, putting the probe into a safe mode that allows engineers to figure out and identify the problem. But in this case, Voyager 1 carried on with its operations without entering safe mode, adding more to the intrigue. It was discovered that the altitude and articulation control system has been sending telemetry data through an onboard computer that has stopped working for years now. This old computer, which should not have been involved in data processing, has somehow become tangled in the telemetry transmission process, leading to the corruption of the message sent to Earth. The task now is to fix this anomaly and determine whether the encounter with the 500 strange objects was real or not. Renowned astrophysicist deGrasse Tyson examined the data, ran simulations, communicated with other physicists, and considered a variety of interpretations. None of them, however, could explain the presence of the unexplained objects that Voyager 1 discovered while traveling through the universe's infinite emptiness. NASA does not yet know when this problem began or how long it will persist. The main concern is what might have caused the communication breakdown. The anomalies affecting the probe. After 46 amazing years of travel, NASA's Voyager 1 spacecraft has experienced a computer malfunction that has caused a communication breakdown with its mission team on Earth. Engineers at NASA's Jet Propulsion Laboratory believe the Voyager 1 spacecraft has been sending nonsensical data due to corrupted memory hardware in the spacecraft's Flight Data System, FDS. The team suspects that a single chip responsible for storing part of the affected portion of the FDS memory isn't working, NASA wrote in an update. FDS collects data from Voyager's science instruments, as well as engineering data about the health of the spacecraft, and combines them into a single package that's transmitted to Earth through one of the probe's subsystems, the Telemetry Modulation Unit (TMU), in binary code. FDS and TMU have been having trouble communicating with one another. As a result, TMU has been sending data to mission control in a repeating pattern of ones and zeros. NASA's engineers aren't quite sure what corrupted the FDS memory hardware. They think that either the chip was hit by an energetic particle from space, or that it's just worn out after operating for 46 years. Voyager 1 launched in 1977, less than a month after its twin probe, Voyager 2, began its own journey to space. The probe ventured into interstellar space in August 2012, becoming the first spacecraft to leave the heliosphere. The problem first began in May 2022, when the probe suddenly started sending nonsensical attitude articulation and control AACS data. Engineers resolved the issue by sending the telemetry data through one of the spacecraft's other computers. In December 2023, Voyager 1 started speaking gibberish again. On March 1st, the team sent a poke to the spacecraft's data system, a command that gently prompts FDS to try different sequences in its software package in an effort to pinpoint the corrupted section. 2 days later, Voyager 1 sent a signal that contained a readout of the entire FDS memory, which helped the team pinpoint the source of the glitch by comparing this memory readout with a previous one to look for discrepancies in the code. Using the readout, the team has confirmed that about 3% of the FDS memory has been corrupted, preventing the computer from carrying out normal operations, NASA wrote in its update. The engineers are hoping to resolve the issue by finding a way for FDS to operate normally without the corrupted memory hardware, enabling Voyager 1 to begin transmitting data about the cosmos and continue its journey through deep space. It takes 22.5 hours for a radio signal to reach Voyager 1, and it takes an equally long time to receive a response. It also means figuring out the exact cause of the glitch is mostly educated guesswork. It could be damaged, or it could be a matter of age. Engineers can't determine with certainty what caused the issue. Two possibilities are that the chip could have been hit by an energetic particle from space, or that it simply may have worn out after 46 years. Rumors are surfacing that the space probe was attacked and the memory was affected. How true is this? And how did NASA fix this aging probe? NASA's Interstellar Amazing Rescue. According to NASA, the team has tried restarting the FSD, but that did not help the situation at all. The team is looking for a solution by examining old documents and making sure to not overwrite essential code. A difficulty with fixing the problem is the length of time it takes to deliver and receive messages. The fixes have been minimal. However, there are more ambitious fixes yet to be announced. As of now, the team has no plans to retire the mission. It's not easy to diagnose and fix problems from 15.1 billion miles away, but NASA is trying. NASA technicians must work within the framework and technology available to their predecessors in the 1970s, sometimes forcing some creative software workarounds. Another update came in October 2023, with a software patch to help ultimately solve that issue and also prevent residue buildup on the probe's thrusters. But these kinds of updates don't come quickly. As a result, it takes time for the team to understand how a new command will affect the spacecraft's operations in order to avoid unintended consequences. Despite all the information on the ground, some may not yet know what Voyager 1 is and what its functions are. Exploring the aging spacecraft. Humans have always looked at the heavens and wondered about the nature of the objects seen in the night sky. With the development of rockets and the advances in electronics and other technologies in the 20th century, it became possible to send machines, animals, and people above Earth's atmosphere into outer space. Well before technology made these achievements possible, however, space exploration had already captured the minds of many people, not only aircraft pilots and scientists, but also writers and artists. Voyager 1 is a space probe launched by NASA on September 5, 1977, as part of the Voyager program to study the outer solar system and the interstellar space beyond the Sun's heliosphere. It communicates through the NASA Deep Space Network, known as DSN, to receive routine commands and transmit data to Earth. Real-time distance and velocity data is provided by NASA and JPL. At a distance of 162.7 astronomical units from Earth as of April 2024, it is the most distant human-made object from Earth. When Voyager 1 launched a mission to explore the outer planets in our solar system, nobody knew how important the probe would still be 45 years later. The probe has remained operational long past expectations and continues to send information about its journeys back to Earth. During the 1960 ES, a grand tour to study the outer planets was proposed, which prompted NASA to begin work on a mission during the early 1970 ES. Information gathered by the Pioneer 10 spacecraft helped Voyager's engineers design Voyager to cope more effectively with the intense radiation environment around Jupiter. However, shortly before launch, strips of kitchen-grade aluminum foil were applied to certain cabling to further enhance radiation shielding. Initially, Voyager 1 was planned as Mariner 11 of the Mariner program. Due to budget cuts, the mission was scaled back to be a flyby of Jupiter and Saturn and renamed the Mariner Jupiter-Saturn probes. As the program progressed, the name was later changed to Voyager, since the probe designs began to differ substantially from previous Mariner missions. Voyager 1 reached interstellar space in August 2012 and is the most distant human-made object in existence. Launched just shortly after its twin spacecraft, Voyager 2, in 1977, Voyager 1 explored the Jovian and Saturnian systems, discovering new moons, active volcanoes, and a wealth of data about the outer solar system. Voyagers 1 and 2 were designed to take advantage of a rare planetary alignment that occurs only once every 176 years and remain the most well-traveled spacecraft in history. Both spacecraft carry a sort of time capsule called the Golden Record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the story of our world to extraterrestrials. The radio communication system of Voyager 1 was designed to be used up to and beyond the limits of the solar system. The communication system includes a 12-foot diameter high-gain Cassegrain antenna to send and receive radio waves via the 3 deep space network stations on Earth. The spacecraft normally transmits data to Earth over Deep Space Network Channel 18 using a frequency of either 2.3 or 8.4 gigahertz, while signals from Earth to Voyager are transmitted at 2.1 gigahertz. When Voyager 1 is unable to communicate directly with the Earth, its digital tape recorder, known as the DTR, can record about 67 megabytes of data for transmission at a later time. As of 2023, signals from Voyager 1 take over 22 hours to reach Earth. Unlike the other onboard instruments, the operation of the cameras for visible light is not autonomous, but rather controlled by an imaging parameter table contained in one of the onboard digital computers, the Flight Data Subsystem (FDS). Since the 1990s, most space probes have been equipped with completely autonomous cameras. The Computer Command Subsystem (CCS) controls the cameras. The CCS contains fixed computer programs, such as command decoding, fault detection and correction routines, antenna pointing routines, and spacecraft sequencing routines. This computer is an improved version of the one that was used in the 1970s Viking orbiters. The Attitude and Articulation Control Subsystem, AACS, controls the spacecraft's orientation. It keeps the high-gain antenna pointing towards the Earth, controls attitude changes, and points to the scan platform. The custom-built AACS systems on both Voyagers are the same. Voyager 1 has 3 radioisotope thermoelectric generators mounted on a boom. Each MHW RTG contains 24 pressed plutonium-238 oxide spheres. The RTGs generated about 470 W of electric power at the time of launch, with the remainder being dissipated as waste heat. The power output of the RTGs declines over time due to the 87.7-year half-life of the fuel and degradation of the thermocouples, but the craft's RTGs will continue to support some of its operations until 2025. The Voyager missions took advantage of a special alignment of the outer planets that happens just once every 176 years. This alignment allows spacecraft to gravitationally slingshot from one planet to the next, making the most efficient use of their limited fuel. NASA originally planned to send 2 spacecraft past Jupiter, Saturn, and Pluto, and 2 other probes past Jupiter, Uranus, and Neptune. Budgetary reasons forced the agency to scale back its plans, but NASA still got a lot out of the 2 Voyagers it launched. Voyager 2 flew past Jupiter, Saturn, Uranus, and Neptune, while Voyager 1 focused on Jupiter and Saturn. Recognizing that the Voyagers would eventually fly to interstellar space, NASA authorized the production of 2 golden records to be placed on board the spacecraft. Sounds ranging from whale calls to the music of Chuck Berry were placed on board, as well as spoken greetings in 55 languages. The 12-inch wide, gold-plated copper discs also included pictorials showing how to operate them and the position of the sun among nearby pulsars, in case extraterrestrials someday stumbled onto the spacecraft and wondered where they came from. Both spacecraft are powered by 3 radioisotope thermoelectric generators, devices that convert the heat released by the radioactive decay of plutonium to electricity. Both probes were outfitted with 10 scientific instruments, including a 2-camera imaging system, multiple spectrometers, a magnetometer and gear that detects low-energy charged particles and high-energy cosmic rays. Mission team members have also used the Voyager's communication system to help them study planets and moons, bringing the total number of scientific investigations on each craft to 11. According to NASA Jet Propulsion Laboratory (JPL), Voyager 1 has enough fuel to keep its instruments running until at least 2025. By then, the spacecraft will be approximately 13.8 billion miles away from the Sun. Although this discovery is intriguing, it is not the first major accomplishment made by Voyager 1. Voyager 1, touring the cosmos. Voyager 1's launch almost failed because Titan's LR-91 second stage shut down prematurely, leaving 540 kilograms of propellant unburned. Recognizing the deficiency, the Centaur stage's onboard computers ordered a burn that was far longer than planned in order to compensate. Centaur extended its own burn and was able to give Voyager 1 the additional velocity it needed. At cutoff, the Centaur was only 3.4 seconds from propellant exhaustion. If the same failure had occurred during Voyager 2's launch a few weeks earlier, the Centaur would have run out of propellant before the probe reached the correct trajectory. Jupiter was in a more favorable position vis-à-vis Earth during the launch of Voyager 1 than during the launch of Voyager 2. Voyager 1's initial orbit had an aphelion of 830 million miles, just a little short of Saturn's orbit of 880 million miles. Voyager 2's initial orbit had an aphelion of 580 million miles, well short of Saturn's orbit. Voyager 1 began photographing Jupiter in January 1979. Its closest approach to Jupiter was on March 5, 1979, at a distance of about 217,000 miles from the planet's center. Because of the greater photographic resolution allowed by a closer approach, most observations of the moons, rings, magnetic fields, and radiation belt environment of the Jovian system were made during the 48-hour period that bracketed the closest approach. Voyager 1 finished photographing the Jovian system in April 1979. The discovery of ongoing volcanic activity on the moon Io was probably the greatest surprise. It was the first time active volcanoes had been seen on another body in the solar system. It appears that activity on Io affects the entire Jovian system. It appears to be the primary source of matter that pervades the Jovian magnetosphere, the region of space that surrounds the planet and is influenced by the planet's strong magnetic field. Sulfur, oxygen, and sodium apparently erupted by Io's volcanoes and sputtered off the surface by the impact of high-energy particles, were detected at the outer edge of the magnetosphere of Jupiter. The 2 Voyager space probes made a number of important discoveries about Jupiter, its satellites, its radiation belts, and its never-before-seen planetary rings. The gravitational assist trajectories at Jupiter were successfully carried out by both Voyagers, and the 2 spacecraft went on to visit Saturn and its system of moons and rings. Voyager 1 encountered Saturn in November 1980, with the closest approach on November 12, 1980, when the space probe came within 77,000 miles of Saturn's cloud tops. The space probe's cameras detected complex structures in the rings of Saturn, and its remote sensing instruments studied the atmospheres of Saturn and its giant moon, Titan. Voyager 1 found that about 7% of the volume of Saturn's upper atmosphere is helium, compared with 11% of Jupiter's atmosphere, while almost all the rest is hydrogen. Since Saturn's internal helium abundance was expected to be the same as Jupiter's and the Sun's, the lower abundance of helium in the upper atmosphere may imply that the heavier helium may be slowly sinking through Saturn's hydrogen. That might explain the excess heat that Saturn radiates over energy it receives from the Sun. Winds blow at high speeds on Saturn. Near the equator, the Voyagers measured winds about 500 mph. The wind blows mostly in an easterly direction. The Voyagers found aurora-like ultraviolet emissions of hydrogen at mid-latitudes in the atmosphere and auroras at polar latitudes above 65 degrees. The high-level auroral activity may lead to the formation of complex hydrocarbon molecules that are carried toward the equator. The mid-latitude auroras, which occur only in sunlit regions, remain a puzzle since bombardment by electrons and ions, known to cause auroras on Earth, occurs primarily at high latitudes. Both Voyagers measured the rotation of Saturn over the course of a day at 10 hours, 39 minutes, and 24 seconds. Voyager 1's mission included a flyby of Titan, Saturn's largest moon, which had long been known to have an atmosphere. Images taken by Pioneer 11 in 1979 indicated the atmosphere was substantial and complex, further increasing interest. The Titan flyby occurred as the spacecraft entered the system to avoid any possibility of damage closer to Saturn, compromising observations, and approached to within 4,000 miles, passing behind Titan as seen from Earth and the Sun. Voyager's measurement of the atmosphere's effect on sunlight and Earth-based measurement of its effect on the probe's radio signal were used to determine the atmosphere's composition, density, and pressure. Titan's mass was also measured by observing its effect on the probe's trajectory. The thick haze prevented any visual observation of the surface, but the measurement of the atmosphere's composition, temperature, and pressure led to speculation that lakes of liquid hydrocarbons could exist on the surface. Because observations of Titan were considered vital, the path chosen for Voyager 1 was designed around the optimum Titan flyby, which took it below the south pole of Saturn and out of the plane of the ecliptic, ending its planetary science mission. Had Voyager 1 failed or been unable to observe Titan, Voyager 2's trajectory would have been altered to incorporate the Titan flyby, precluding any visit to Uranus and Neptune. The route Voyager 1 was launched into would not have allowed it to continue on to Uranus and Neptune, but could have been altered to avoid a Titan flyby and travel from Saturn to Pluto, arriving in 1986. On February 14, 1990, Voyager 1 took the first family portrait of the solar system as seen from outside, which included an image of planet Earth known as Pale Blue Dot. Soon afterward, its cameras were deactivated to conserve energy and computer resources for other equipment. The camera software has been removed from the spacecraft, so it would now be complex to get them working again. Earthside software and computers for reading the images are also no longer available. On February 17, 1998, Voyager 1 reached a distance of 6.4 billion miles from the Sun and overtook Pioneer 10 as the most distant spacecraft from Earth. Traveling at about 11 miles per second, it has the fastest heliocentric recession speed of any spacecraft. As Voyager 1 headed for interstellar space, its instruments continued to study the solar system. Jet Propulsion Laboratory scientists used the plasma wave experiments aboard Voyager 1 and 2 to look for the heliopause, the boundary at which the solar wind transitions into the interstellar medium. As of 2013, the probe was moving with a relative velocity to the Sun of about 61,197 kilometers per hour. With the velocity the probe is currently maintaining, Voyager 1 is traveling about 325 million miles per year, or about 1 light-year per 18,000 years. Voyager 1 left the heliosphere, the giant bubble of charged particles that the Sun blows around itself, in August 2012, popping free into interstellar space. The discovery was made public in a study published in the journal Science the following year. The results came to light after a powerful solar eruption was recorded by Voyager 1's plasma wave instrument between April 9th and May 22nd, 2013. The eruption caused electrons near Voyager 1 to vibrate. From the oscillations, researchers discovered that Voyager 1's surroundings had a higher density than what is found just inside the heliosphere. It seems contradictory that electron density is higher in interstellar space than it is in the Sun's neighborhood. But researchers explained that at the edge of the heliosphere, the electron density is dramatically low compared with locations near Earth. Researchers then backtracked through Voyager 1's data and nailed down the official departure date to August 25, 2012. The date was fixed not only by the electron oscillations, but also by the spacecraft's measurements of charged solar particles. On that fateful day, which was the same day that Apollo 11 astronaut Neil Armstrong died, the probe saw a 1,000-fold drop in these particles and a 9% increase in galactic cosmic rays that come from outside the solar system. At that point, Voyager 1 was 11.25 billion miles from the Sun, or about 121 astronomical units. 1 astronomical unit is the average Earth-Sun distance of about 93 million miles. Since flying into interstellar space, Voyager 1 has sent back a variety of valuable information about conditions in this zone of the universe. Its discoveries include showing that cosmic radiation out there is very intense and demonstrating how charged particles from the Sun interact with those emitted by other stars. Mission Project scientist Ed Stone of the California Institute of Technology in Pasadena told Space.com in September 2017. The spacecraft's capabilities continue to astound engineers. In December 2017, for example, NASA announced that Voyager 1 successfully used its backup thrusters to orient itself to talk with Earth. The trajectory correction maneuver thrusters hadn't been used since November 1980, during Voyager 1's flyby of Saturn. Since then, the spacecraft has primarily used its standard attitude control thrusters to swing the spacecraft in the right direction to communicate with Earth. As the performance of the attitude control thrusters began to deteriorate, however, NASA decided to test the TCM thrusters, an idea that could extend Voyager 1's operational life. That test ultimately succeeded. With these thrusters that are still functional after 37 years without use, we will be able to extend the life of the Voyager 1 spacecraft by 2 to 3 years. Voyager project manager Suzanne Dodd of NASA's Jet Propulsion Laboratory in Southern California said in a statement in December 2017, "Mission team members have taken other measures to extend Voyager 1's life as well. For example, they turned off the spacecraft's cameras shortly after the pale blue dot photo was taken to help conserve Voyager 1's limited power supply." Over the years, the mission team has turned off 5 other scientific instruments as well, leaving Voyager 1 with 4 that are still functioning. The Cosmic Ray Subsystem, the Low-Energy Charged Particles Instrument, the Magnetometer, and the Plasma Wave Subsystem. Voyager 1's next big encounter will take place in 40,000 years when the probe comes within 1.7 light-years of the star, which is roughly 17.5 light-years from Earth. However, Voyager 1's falling power supply means it will probably stop collecting scientific data around 2025. Thank you for watching. Comment to share what you think in the comment section below. Remember to like and subscribe to see more videos.